Hello, welcome back. I'm Dr. Churchill, and this lecture today is going to be on the science of life in the universe. I like to call it How to Science. And the reason I like to call it How to Science is by the time we're done with it, we're going to go through a simple recipe, if you will, which of course is oversimplified, about how one can look at the structure of the scientific method. So as we get started, I just want to say, have you ever thought about why you think the way you do about the world, even if your thoughts are not really highly educated, you still have this view of the way the world works. And we base that on our five senses, and we try to piece this together. And we have this amazing machine up here, which does a lot of inductive reasoning and inferencing, and puts this material together and makes sense of it. Well, that's the human condition, and that is the human condition for thousands of years since we first had what you might call civilizations or any technology. And what I'd like to do today is go through that story a little bit about how we developed a method, if you will, a recipe for trying to figure out the world, and it developed into something called the scientific method. So that's really what we're going to be focusing on. And in the process, what I want to tell you is every theory that we have is wrong. That's right. Every single scientific theory we have is wrong. Maybe the better way to say it is that it's incomplete. But I wanted to just make a big impact, a splash. The point is, every theory is incomplete because we do not know true reality. We can only continue to probe deeper and deeper and deeper. And what is so amazing, which I hope to do between this lecture and the following lecture, is let you know that even today, even our most sophisticated theories, we not only know they're incomplete, but we're clever enough to know in what way and how they are incomplete. And those little pieces of information, what you might call the fly in the pudding, that's the stuff that's exciting. That's the stuff that tells us where to sniff out the rest of the trail, which way to go, what direction to go, how to think about it, how to ask nature, how to develop new technologies to ask nature. So I would like to take you through this journey before we go into, if you will, out into the universe, which will be our module 3. Having said those things, I'd like to bring you to the slides. And so I'm going to go ahead and share my screen so that we can take a look at that. Okay, hopefully now you can see that I've got slides set up. And what we have here is the beginning of chapter 2, the science of life in the universe. And really, that's a misnomer. It's really about how do we science. So that's why I call it How to Science. Okay, what I'd like to show you first of all is this picture here, which I think is spectacular. That was taken back in the 1980s, which may seem like ancient history to you right now, but I was in college in the 1980s. And this was a very special moment. We had science fiction stories like something called Buck Rogers, if you've ever heard of that. And so Buck Rogers would fly around on his jetpack in space. Well, by 1980, we're flying around in jetpacks in space. And that was a pretty spectacular situation. This astronaut here is in orbit around the Earth with no tethers. He himself is a satellite of the Earth. He's moving at about 18,000 miles per hour. And basically in free fall around the planet. But he's moving so fast along the surface of the planet that as he falls, the curvature of the planet is moving out from underneath the astronaut. And so what we have is that they end up never actually striking the Earth. They end up going around it. This is called an orbit, and it's a trade-off between the inertial motion of the astronaut that's sideways and the gravitational force pulling down on the astronaut. And this is an amazing balancing act. And I think there's a lot of you who would say, I would never be caught dead in that picture like that. I don't have the bravery, or you might think, I don't have the faith in the technology of the people that built the spacesuit keeping me alive, or built the jetpack that can get me back to the spacecrafts where I can go home and be safe. Or do I have faith in Newton's law of gravity or Einstein's laws of gravity enough that I would put myself out there and risk my life based upon a theory about how I should move? So those are great questions that we learn a lot about ourselves if we really think about what our personal answers to those questions can be, because we're learning a great deal about whether we believe science or believe in science. And that gets me back to that magic word believe in lecture 1. I mean, at some level, we have theories, and we also have a belief system that goes along with those theories. But I want you to remember what I said was that when a scientist says the word belief, they're really basing it upon a lot of logical inferences. They've ruled out all of the other possibilities, and this is the one left standing that they are going to choose to believe in. And then I come back to the fact that all of our theories are incomplete and therefore, in a sense, kind of wrong. And so why would you believe in something that's wrong? So that's the other part to the word believe. It's basically using a structure of something at the current time, like a theory or an idea or a hypothesis, to help you learn the next step, okay? And then you might believe in it enough to be brave enough to be like that astronaut. You know, that's all the difference for each of us. So what I'd like to do is go through this story today and talk about some famous people in science. So I'm going to go ahead and move to the next slide for you. Okay, so here's some of our learning goals. We are going to be talking about an ancient debate about life a little bit in this segment, but we're going to kind of leave that for some later chapters. But for the most part, we're going to go back through and talk about the story of how we learned how to do science, and we're going to use astronomy to do that. And really, the reason is that because astronomy was always at the center of human wonder and human observation and human questions. And so astronomy really was, in a sense, the first science, looking at the sky and trying to make sense of it and getting it wrong for a long time, and then figuring out how to learn how to get it right. Okay, so we're going to talk a little bit about that. Now, we are going to learn the story from the Western point of view. And I think the reason is that we're not going to include a lot of different cultures in this process. We talk about it is because science today has really been a Western-driven phenomenon. And in that sense, since it's been the predominant culture, it looks back at its own history. It looks back at its own, lineage of its own culture. And so today we are going to talk about the lineage of Western science. Now, that's not to say that there weren't a lot of other parts of the world that had great science. In fact, we're not going to talk about the Middle East scientists today. And well, we sort of do a little bit, because we're going to talk about a fellow named Ptolemy who comes from the Middle East. But for the most part, we're going to be talking about the Greeks and some Western, Northern European and Southern European people. But there was a tremendous science in China. There was tremendous science in the Middle East. And there was even amazing astronomy in the Americas before all of that information got wiped out about 400 years ago. Sometimes I think it's pretty tragic, because imagine if everything we knew about the Greeks and the Romans got wiped out because the Americans had come over to Europe and destroyed all those civilizations. And so I feel like sometimes half of all of human knowledge may have been eradicated through this process, kind of a genocide process. And it's horrible. And I wish that we could have a more holistic view of this, and hopefully we can recover as much as possible, and in the future have a much more broader view of everything. But today, even in 2020, we still will be talking about the Western society version of science. Okay, now, so we'll talk about what the Greeks argued and what they thought and why they thought it, and it brings in philosophy by nature, and because there wasn't a lot of experiment in those days. Then we're going to move on through to this fellow Ptolemy, who's going to refine the Greeks' work, and move on then to the Copernican Revolution and Copernicus. And this is going to be another, if you will, major component of our discussion, is that we're going to talk about theories or hypotheses and theories and models of the way things work. You know, a model is not a complete theory, but just kind of a picture, if you will, of how things work. And how those get completely wiped out, and they're so wrong that they just get swept away and a whole new vision replaces them. And that's what we call a paradigm shift. So a paradigm is the way we see the world, and how we develop all of our ideas. And then sometimes we realize they were so wrong, they get swept away, and we develop a whole new set of ideas of how things work, and we start building on those. And so one paradigm gets replaced with a new paradigm. And I'll try to make more sense of this later as we go through this. And we call this a paradigm shift, and sometimes we call it a revolution. Okay, we've had several revolutions that we're going to talk about in the next two segments here, or modules, 2A and 2B. Okay, so how did this change our perspective, this Copernican revolution that happened? Okay, all right. I'm not going to get into it. How do we distinguish science from non-science? It's in the book, but I certainly will talk about what is a scientific theory. And then this latter part, gravity, is really going to be our focal point for 2B, module 2B. And that is going to be a way that we're going to really talk about looking at the world in new ways. So two paradigm shifts that happened just due to gravity are tremendous. That we're going to talk about Isaac Newton, and everybody's probably heard of Albert Einstein. I'm also going to talk about James Maxwell, whom probably most of you have not heard of unless you're a physics major, but we'll be talking about some of these things. Okay, so we're going to look at a historical perspective. We're going to tell a story. That's what we're doing here. We're going to tell a story that's going to show you how piece by piece we just got better at it and got better at it, okay? What I want you to do is look at the red writing at the bottom of this slide. It says, science and its history teach us that we can never actually know the truth or have a complete and total correct theory. We can only continue to improve on our understanding of nature and the universe, and every step of the way we're sitting on our best theory or honing our best theory, and usually can find flies in the ointment to realize that we understand it's incomplete. And that's when it's exciting. That's when new things can be learned. Okay, so let's start with the Greeks. With the Greeks, they didn't have experimentation, but about 500 years before the Common Era, there was this point in Athens, and particularly of Greece, where the number of geniuses in one city was just, off the charts. And you had people like Pericles, and you had Plato, Socrates, Archimedes. I could name a lot more that did, like the Democritus and Hipparchus, but we're just going to really talk about Aristotle, who was a student of Plato's. And Aristotle was the first person to sort of codify, if you will, what he thought the universe was, and from the Western culture foundations. Now, from Plato, who was Aristotle's teacher, had said, basically, the universe must appeal to our perfection, sense of perfection. And a sense of perfection was that everything in the universe would be constant, unchanging, immutable, pure, and that geometrically, because they understood geometric figures very well, circles, cones, ellipses, parabolas, that the most perfect geometric form was the circle, and therefore it would be their conclusion that the circle must reign supreme in the heavens. So I want you to, here's the list. It's like everything was perfect, nothing ever changed, and the circle and the sphere reign supreme in the universe. Okay, so here we have it, as I have on my slide. The circle is the most perfect form, the sphere, the extension of the circle. And there was some evidence that that should be the case. If they watched the stars over the course of the night, this is a 6-hour exposure from a camera with the shutter left open, you can see that it seems that the circle is the arc that's traced out by the stars every night. Now, this is pretty interesting if you look at this photograph, because if you didn't know, if you hadn't been told by the scientists that in fact it's the Earth spinning on its axis that makes the universe look like it's going around us because we're rotating, okay? The Greeks, they didn't know the Earth was moving, and they had no reason to assume it was. So what did they think? They thought, in fact, that the whole universe was rotating around the Earth, and that given the symmetry of the situation as they could see it, the Earth must be at the center, okay? So the Greeks said the Earth is at the center, Aristotle said, at the center of the universe, and that the universe rotates around the Earth, okay? So this whole idea of spheres and perfect motion, okay, and I want you to understand as a corollary to the perfect motion for the rotation of the universe around the Earth, which is a wrong theory, just so you remember, that the speed of that rotation would have to be the same. It would have to be constant, okay? And not only would it have to be constant, it would have to be constant for all time, forever, 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 forever more, okay? Nothing ever changes, and it all is on spheres. So they thought the stars were on these big spheres, this big sphere they call the celestial sphere, okay? This idea is pretty sophisticated thinking to some level, but it reigned supreme for 2,000 years. Think about that. We thought the Earth was at the center of the universe for 2,000 years and thought that pretty much that the stars were on a sphere that orbited, if you will, rotated around the Earth, okay? Now, this whole model was built upon this sense of symmetry in time, symmetry in motion, and symmetry in geometric forms. So it developed from a sense of beauty. That was Aristotle's idea of aesthetic beauty. And so it's a very interesting thing that we planted into the very fabric of of trying to understand the universe, that it was a beautiful, symmetric type of entity. And that has never been replaced. I want you to understand that. The sense that every scientist feels that fundamentally down deep, the universe has to be beautiful, it has to be symmetric, okay? These things are key to even the way we think and the way we develop theories today, which is why I asked you earlier, do you ever wonder why you think the way you think? Well, if you have any sense of thinking the universe is beautiful, it really fundamentally has come all the way from the Greeks. Okay, so again, this reigned supreme for 2,000 years, and nobody really questioned it too much, okay? But again, People found flies in the ointment. We'll talk about those next slide. Now, Aristotle, again, was somewhere around 350 before the Common Era, and he developed this geocentric model. Geocentric, geo meaning earth, centric meaning the center, so geocentric means the earth-centered model. And you can see it here in the upper right corner. We have the earth at the center, and we have the celestial sphere of stars that rotate around the earth in the outer sphere. But Plato had to take care of the wanderers, or the planets, as they call them. Okay, these were bright objects that seemed to move across the sky. And at their time, they only knew 6. And so he had to put them on spheres that rotated around the earth, but were inside the sphere that the stars rotated on. So he had basically the moon, and then Venus, and then the sun, and then Mars, et cetera, et cetera. So you can see actually the true picture here, looking down on this model here, is it was moon, Mercury, Venus, sun, and then Mars, Jupiter, and Saturn, and then the fixed stars. Okay, and these were spheres that moved at constant speeds. So the Earth is at the center and non-moving. The planets are locked onto these spheres that rotate. They were immutable. They were perfect crystalline material. Okay, and the stars were locked on the most outer sphere called the celestial sphere. All motions were circular because they're carried on a sphere, and so that's the one or two-dimensional version of the sphere is a circle, and they all moved at constant speeds. And everything beyond Earth was perfect, and everything beyond Earth never changed. Okay, I think I've said that many times over, and the reason I'm doing that is because the rest of the lecture is going to be about tearing this down. Okay, one by one, people are going to notice things like, oh my gosh, things do change out there in the universe with time. Oh my gosh, things don't move at constant speeds out there in the universe with time. And so you start whittling away and understanding the incorrect parts of Aristotle's geocentric model or theory. And one by one, it gets weaker and weaker and weaker. And then we're going to see that Copernicus came along and sweeps it away. Okay? All right. So now, something also interesting happened here. The Earth at the center is also an outcrop of another human-centric notion. It's our ego that says this universe was built for us. It was built for the Earth. It was built for humans to live on the Earth. And they didn't understand any of the things we know today about that they evolved and things like this. Okay, they thought as far as they knew, they were placed here by gods, and this was all created for the sake of humanity. And that also got into our system, and it's stuck around for over 2,000 years. And in fact, it still persists in a lot of people. Okay. Now, given that, there would be no reason to believe that there was life elsewhere in the universe. And so the Greeks really did not believe that there was life elsewhere in the universe. In general, there of course were some dissenting views of some radical thinkers of the day, but they were minority voices and didn't make it into the long historical arc of what we're going to talk about. Okay, so let's start talking about the first fly in the ointment, the first little piece of evidence. In other words, somebody looked up at the sky, saw some stuff, and the stuff they saw didn't quite, behave the way that Aristotle said it should behave. All right, so the first observation that people saw was something that we're going to call retrograde motion. Okay, and this is the backward movement of the planet on the sky. Okay, what? You said that the planets were all on spheres and rotating around the Earth at constant speed. How can they go backwards and go forwards if they're at constant speed? Okay, so this is a problem for Aristotle's model. Okay, And in a sense, what you see, you know, a planet coming across, going like this, and then they observed it slow down, come back, and then do that across the sky. Now that is a serious problem for the idea that it's going at constant speed on the surface of a sphere. So Ptolemy decided to try and explain this. Now, Ptolemy was an astronomer, and he was in Egypt, in Alexandria, and he was a descendant of one of the generals of Alexander the Great, thus the name Alexandria for the city. And he was a descendant of one of the generals who got a fourth of Alexander the Great's empire, and that included Egypt. And so this was an area where there was a lot of leftover Greek thinking, what they called Hellenistic thinking and science, that mixed in with the Middle Eastern world too. And Ptolemy was one of the pinnacle scientists of the time and the curator of the library of all this information. And he was well familiar with Aristotle's picture. Now, this is about 400 or 500 years after Aristotle that Ptolemy existed. So Ptolemy noticed this movement of the planet. He wasn't the first, but he was the first to think about it. And bada bing, it rotated around and then went back on its merry way. Okay, now, he decided that he had to do something and add something to Aristotle's model to make it work. But he adopted every single thing about Aristotle's model. The Earth's at the center, things move at constant speeds, and they move along circles. So to get Mars to do a loop-de-loop in the sky, so to speak, he put an extra circle on top of the circle that Mars is on, okay? So circles on circles. So in this diagram down here, this is the circle that Aristotle said Mars moved along. Ptolemy put an extra circle here and put Mars on that circle, and he had this circle spin around some imaginary point connected to the main sphere on which Mars was being carried along. And so then Mars would do these little loop-de-loops. And so what would happen is that as this thing's rotating and moving along, okay, the path of Mars then ends up looking something like this. And what you get is you get this little loop-de-loop motion. And everything about Aristotle's model still holds. Again, he didn't push against the model. He added an extra layer to the model. And that's important because he's not changing our view of the universe. He's adapting our view of the universe and just adding some more information to it, okay? This is what we call refinement, okay? This is refinement of a current model. That's a very important word, it's refinement, okay? And so this is the first indication that we have this process called refinement in scientific thinking. And he developed a mathematical model for the exact path of these planets. In fact, to get his motion of Mars to work out so that it matched what he observed, he had to put multiple circles on the circles. So this circle was on the main Mars orbit. Then he had a circle on this one and a circle on that one. He went up to 9 circles, okay? Imagine doing the mathematics to keep track of the motion of a point on the 9th circle as it rotated around on the 8th circle, which rotated around on the 7th, which rotated around on the 6th, et cetera, et cetera, et cetera. But he did. He wrote down all the mathematical equations for that and was able to predict the motion of Mars. And it did pretty well. I mean, if you put all that complicated stuff in there, you could just keep adding complicated layers till you get it right. That's what he did. And we're going to learn that that's not the path we want to follow. We don't want to make it more and more and more complex. We want to make it more simple because we believe it's beautiful and simple, okay? So he was able to put together this very complex model of his mathematics. And I want you to understand something. This is the first time in human history that mathematics was used to make a prediction about how the universe should behave. He could predict with his model, and it's all his math, where Mars was going to be in 2 years, where it would be in 3 years, where it would be in 4 years, where it was 25 years ago, okay? That is the first time that ever happened. It's highly sophisticated, and that is a very important shift in the step forward of human knowledge and development of technology and the world we have today. There is a little video here that you can link to. I actually have it up on the module. It's video 1 called Retrograde Motion and the Opposition of Mars. It's pretty good, okay? But you know, if you want to Google or go into YouTube and just Google retrograde motion or things like that, or Ptolemy, you can get a whole bunch of neat information. There's a lot of good stuff out there. Okay, so we have our first refinement. It's very complex, and it's our first mathematical model. Okay, now not a whole lot happens because we start to enter the Dark Ages around 450 or so, give or take. The Roman Empire falls, and we're basically have this set of kingdoms that splinter all of Europe, and then you have an empire to the east called the Byzantine Empire, which preserved a lot of those Roman ideas. So that's why we have them today. But effectively, you had 1,000 years of Dark Ages from around 300 Common Era to about 1300 Common Era. And then people started to slowly awaken. And one of the reasons that Western Europe started to awaken is because all of those ideas that were preserved in the Byzantine Empire, which was centered in Constantinople and Turkey, started to migrate their way back into Western Europe. And that reawakened, or was one of the factors that reawakened Europe. Okay, enter a period of time which is going to be called the Renaissance. People that you've heard of, Galileo, Leonardo da Vinci. Somebody that you may or may not have heard of is Nikolai Copernicus. He was a mathematician, astronomer, and a monk. He was living up in Poland, and he spent a lot of time thinking about retrograde motion and Aristotle and planetary data. And so he really came up with this notion that he could make the same predictions effectively, or almost as accurate predictions about the planets that Ptolemy had made, you know, almost 1,500 years earlier, okay? If he put the sun at the center and let the planets orbit around the sun, okay? This is called the heliocentric model of the universe. And, excuse me, really, Copernicus had no real new data on which to make this bold leap in thinking. He just realized that the mathematics came out much simpler and much cleaner. And that appealed to him and others because it was beautiful and simple, just like Plato and Aristotle believed in. And Ptolemy is the one who had made this universe or solar system so complex. Okay, so he said, I'm going to put the sun at the center. I'm going to put then Mars and Venus and then the Earth. I'll let the moon still go around the Earth, and then, you know, Mars and Jupiter and Saturn and whatnot. And I'm going to work all the math there. And he could explain retrograde motion. He could explain that backward loop-de-loop and in a very, very natural way without having to add circles on circles. And I'll show you this in the next slide. But here's the point I want to make. So please listen to this point. He kept all the orbits as circles. He kept all the motions of the planets as constant. He really, in a sense, still believed in the spheres on which the planets went on, but he just decided to reorder what was going on. Now, the thing about this was he had to assume that the Earth rotates on its axis. And So there's a lot of leaps here, but there's also a lot of firmly keeping your feet planted in the old model, the old theory. Okay, so it's interesting because even though it's a revolutionary idea, it still had kind of one foot in Aristotle's, worldview. Perfect spheres, constant motions. Okay, but that's something that I want to really point out here, is that even though he completely changed our view of where the Earth is and had it rotating and had these leaps of intuition, if you will, to change our worldview of where the Earth and the Sun are and whatnot, and I'll get into the implications for that in a minute, but he did it with one foot stepping out of Aristotle's old box, which is beauty and symmetry and unchanging motions. Okay, so he still had the planets going in circles on spheres. Okay, now one of the things that was really important about this idea was that it dethroned humanity from the very center of the universe, and a lot of people had trouble with that, particularly after 1,000 years of having this indoctrinated in them by the greatest political power that existed for those 1,000 years, which was the Roman Catholic Church. In fact, he published his book, Copernicus did, after he died, so that he would not be effectively asked to come down and be given an inquisition, perhaps tortured and killed for this heresy of an idea that humans and Earth were not at the center of the universe, and that the universe therefore was not centered about humans. Okay, so that's what's in the red box down here. Now I want to talk to you about how he was able to use this simpler model to explain retrograde motion. Okay, now again, I've got a nice little video on this. It's called it's the retrograde motion video, right? So even though I have another link here, I have a different movie on the module online, but you can always look at these links too. Okay, here's the link down here. All right, so how do we explain this? Okay, so this is one of those situations where you're now on a moving platform, okay? And Mars is now orbiting this. So we're on a moving Earth, and let's look at Mars. And remember, retrograde motion is the apparent backward motion of the planet on the sky. Ptolemy said he thought it was a real backward motion because we weren't moving, so it had to be the thing that was doing the loop-de-loop moving. Now we're going to say, no, the loop-de-loop doesn't happen because now it's an apparent illusion that it looks like it's loop-de-looping, okay? So as you can see here, here's the Earth going around its orbit. We are at position 1, say on January, and then each month, February, March, April, all the way to July. If you look at where, in this configuration, Mars might be here in January of our calendar, and we look out on the sky, on the big movie screen on the sky, and we see it over here in the constellation Gemini. Okay, a month later we come back, and we've moved along our orbit. Mars has moved along its orbit, and lo and behold, we see that Mars now appears to have moved over to this, east side of Cancer, all right? Month 3, we've moved along, Mars has moved along, and now we see that we're somewhere between Leo and Cancer, and we see this path along the sky of Mars projected. Now we start to see a change when we're at opposition, when we're both lined up with the sun. At, in this case, would be the 4th month of our story, which if we started in January would be April. Here's Mars, here's Earth, and we see that now Mars was here, and it looks like it's done a loop-de and started to go backwards, okay? And then we come along in May, we've moved along our orbit. Here's Mars along its orbit. We see its projection, and it's over here. And so now, as we've charted it, it's made this motion. And as we start to come around the bend here, Mars is moving along here, and we're moving along here. And that three-dimensional behavior is such that the two-dimensional projection, it looks like now Mars has entered the west side of Leo, And so it's come along this way from month 5 to month 6. And then in month 7, Mars has moved along here. We've moved there. We check the projection, and now Mars is on the east side of Leo. And so it's just a pure optical illusion that Mars looks like it's going across the sky, reversing its orbit, or reversing its direction, which we call the retrograde motion, and then going back along its merry way again. As you saw, Ptolemy thought that Mars is doing circles, and Copernicus says, I'm getting rid of all of that complicated 9 circles going around each other math, and I'm just going to say, look, you can get it straight from my simple, we're going around the sun model, the heliocentric model. Okay, so anyway, this is something where the complicated has been made more simple. This was a revolution of thought. First of all, we revolutionized where we were in the universe. We're no longer at the center. That was a very, very entrenched idea, 2,000 years of that being basically taught and preached, and used as a piece of information to persuade people that the universe was built around us and for us. Okay. The other thing is that we see the world and the universe different now. To embrace the Copernican model, we have to think we're on a spinning planet now. The planet is spinning, because how else do you explain what it looks like the stars going around us? So all of a sudden now we don't have a universe. Think about this. In everybody's mind, the universe went around the Earth. Okay, all of a sudden now people are like, no, that doesn't exist. There's just this sphere out there. It's not moving, but we're rotating around, and so it looks like it's moving. And so you get the daily motion of the sun, you get the daily motion of the stars, and all of that. A huge mental shift in picture. And now with that mental shift, new questions can be brought into the human mind. And that is why it is an important paradigm shift. We went from the geocentric paradigm to the heliocentric paradigm. It's called the Copernican Revolution, and it was the first major shift in human knowledge. It took 2,000 years to get there. As you're going to see, that process begins to accelerate of paradigm shifts. So let me recap what we've got here. And I like to call this Old Dead Guys That Rock Your World. And the reason I call it Old Dead Guys That Rock Your World is because, you know, how many times have I shown pictures of Greeks that have done things, or asked multiple choice questions about Greeks that have done things like, you know, who was the person to first measure that the Earth was a sphere, you know, back in 150 Common Era. And then, of course, we have all these flat earthers still, okay? But, you know, and so many times I put this multiple choice options as some old dead Greek guy, and like 20% of the class would pick that because they couldn't remember the person's name. So I always love the idea that we look at these people like statues, that we look at them as static black and white things. And that's why I'm using these old pictures here, but they're not. They were living, breathing people trying to understand the world at the edge of human knowledge at the time. And they were firmly ensconced in the belief systems of their time. So I just want to bring that out to you, that this process is a living, breathing process. It's an art form. Okay, so we have Aristotle sometime around 350 before the Common Era. We wait another 100 or 400 years, about 150 after the Common Era. We have Ptolemy, and then we wait another 1,500 years for Copernicus. So literally left roughly 2,000 years from Aristotle. He survives, his model, the geocentric model survives, and then Copernicus revolution of the heliocentric model. Okay, Aristotle proposed the geocentric model. Heavens are perfect and unchanging, and perfection is found in circles and spheres. Okay, we talked about that model. Ptolemy built on the geocentric model, refined the geocentric model, explained the apparent backward motion of the planets, called retrograde motion, by adding little spheres on spheres and spheres. It became very complex, but it was the first mathematical, if you will, formulation of understanding the universe. And therefore, in that sense, it was also revolutionary. Okay, but the real revolution came with Copernicus, that he proposed the heliocentric model. Again, that was a leap of intuition because he had no additional data, even 2,000 years later. He explained retrograde motion naturally, in a sense, beautifully, symmetrically, and simply. And that was all a consequence of us being on an orbiting Earth around the sun. Again, I just want to mention that even a paradigm shift of that nature, where you get rid of the rotating sphere around you and that's gone, and we have a whole new view now of the universe, he still kept his feet firmly planted on Aristotle's model in terms of the unchanging cosmos and the constant and perfect motions. Okay, now we have to whittle away at those. Okay, so that brings me to the next stage in this lecture, and it could be that you want to take a little break here, but we're going to move on to the next layer of dismantling the geocentric model. Now, before I step there, I want to say, just because Copernicus wrote down that the sun's at the center doesn't mean that it became accepted by the academic world, and certainly not by the church, which again was the most powerful political entity. They call it the Holy Roman Empire for a reason, okay? And so that took more time, that took more evidence. So we have to chop away at this tree. And so this story now is going to be the chopping away at that tree. We've introduced the idea of the heliocentric model. We have not yet adopted it. We have not said, we believe that that's the best model. Okay. This is a summary of why that scientific revolution was important. And so I just want to talk about the box at the bottom and the two bullets at the bottom. I've already mentioned them, but I had written them down here. I apologize, I'd forgotten I had written them down here. So it was a game changer, okay? We have a radically different universe, but it's still simple and symmetric, okay? So the change from Earth-centric, geocentric, to heliocentric, sun-centered model is an example of this paradigm shift, as I said, completely different view of the universe. Some of the consequences of that were that humanity is no longer the center of the universe. And that starts a whole new revolution in human thought. And then the notion was that we could unlock the nature just by thought, was starting to have some flies in its ointment as well, because it led us down the wrong path. Or we learned it later when we adopted Copernican model that it led us down the wrong path. But that the notion of simplicity and beauty still survive today. So some repeat of what we said before, but written down on a slide for you. Okay, so let's whittle away at the first pillar, if you will, of Aristotle's model, which is that the heavens are not changing. Okay, I'd like to introduce you to a gentleman by the name of Tycho Brahe, who was a Dane, and he wanted to be an astronomer, but his father, of course, wanted him to be in the medical field or be in the legal field, but he wanted to become a science person. And he got famous because he was able to measure the distance to a comet. And he showed that that comet was further away from the Earth than it was from than the moon is. He also was able to make observations of a supernova and determine that the supernova also was in space, that it was not part of the Earth's atmosphere. Now, it used to be that supernovae, which would be sort of these, what they call new stars or novae, new stars, these are stars that we now understand as exploding stars, and they light up for a while and then they disappear. Those were thought to be in Earth's atmosphere. And comets were also thought to be in Earth's atmosphere. And if you think about it, you had to assume they were in Earth's atmosphere because they came and they went. They were what we call ephemeral. They were changing. They would brighten. They would grow a tail if it was a comet and it would go away, or a star would brighten and then go away. It couldn't be out there in the universe because Aristotle said the universe was unchanging. Okay. Tycho Brahe was able to show that the supernova was not in the Earth's atmosphere, but it was very far away. And he was also able to show that this comet was very far away, further than the moon, therefore had to be out in space. Therefore, and here's the key, he discovered two objects that were changing with time, but were out in the cosmos. Now that is going to put a lot of pressure on Aristotle's picture of the universe, okay? This is what we call tension, okay? We have refinement, like what Ptolemy did, but now we have something called tension. These are observations that push back on your theory, that basically say, explain that. Your theory says that shouldn't happen, okay? And it happens, so what's wrong with your theory, okay? In a sense, that's what retrograde motion was. It was tension on Aristotle's theory. And the way that it got resolved was by refinement of making the theory more complex, okay? So now we're faced with another tension on Aristotle's model, and that is that things in the universe can come and go, and they do change, okay? Now, he measured the distance to these things using a phenomenon called parallax. There's a little movie down here, which is a demonstration that I also found another one that I like as well. You can click on this link on the video, on the lecture notes, or you can actually also look at the one that's about a minute long called Stellar Parallax and Measuring Distances, which I think is much nicer. It actually has some explanation that goes with it, whereas this little demonstration down here, it doesn't have any narration. But the idea of parallax is simple as this. If you put your thumb out, look at something way in the distance, and you put your thumb out and you cover one eye, you put your thumb in front of this thing that's in the distance, and then you uncover your other eye and look at it, you'll see that your thumb looks like it's shifted and is no longer in front of that object. And it turns out that the closer your thumb is, the more that shift will be. And it turns out that you can measure the angle of the change in your thumb, and you can therefore measure the distance to your thumb. And so this is the principle by which Tycho Brahe was able to measure the distance to these things. So this is a little picture down here explaining it, though you can watch the video as well. If the Earth is here in January, and then it's here in July, okay? And we look at the background of stars way out there, very, very far away. These are much further. Think of them as being, a mile in the sky above this picture. They're that far away. And then you have this nearby star, which is equivalent to your thumb, in my other analogy. And when you look at it in January, you see, relative to these backgrounds of stars, you see this star over in this area of this star field. So that's what this would look like on the sky. Here's the picture of the star field on the sky, these stars. And then you would see the star in question over here between these three stars. But when you've moved, it's like switching eyes from your left eye to your right eye. When the Earth is moved over here in July, and you look up, you see that the stars over here in this grouping of stars. And so in July, you see that your stars moved over here. And so you can measure this angular distance on the sky, okay? Just like I would measure the angular movement of my thumb, apparent angular movement of my thumb. Even though my thumb's not moving, it looks like it is, okay? And you measure that angle and you can measure the distance, okay? Now, one more thing about this is it only works if the Earth is moving around the sun, okay? if the Earth wasn't moving around the sun, you wouldn't see parallax, because it's kind of like saying, I got one eye here and I never switched to my other eye. So I'd never see this apparent angular motion. Okay, so that was kind of a nice little confirmation for the Copernican view that it was a heliocentric model and the Earth went around the sun. Okay, you can't get this in the geocentric model. So that's kind of nice, a little confirmation of the idea that Copernicus might be onto something, but you know, it also showed the mathematical ability to determine that things in the universe out there change with time. So this made Tycho quite famous. He was given a ton of money by the Danish king. He got to become the court astronomer. He set up an entire castle, and then basically, and he called this castle Sky Dome, and he made these huge, like gigantic, 30 feet on a side spheres with little tick marks for angles and little arrow, a long pole with an arrow on it, and they would rotate it around, and they could rotate it this way, and they could figure out the exact, and point it right into Mars or Jupiter or Saturn, and they could measure the exact position of that planet every single night. And so he took our measurements of where the planets were every night, and he measured them for 10 years, night after night, with a precision which was over 100 to 1,000 times greater than had ever been done before. So after 10 years, he had this spectacular data set. And so his other contribution to humanity, besides poking a hole in this one pillar of Aristotle, which is, you know, saying that things in the universe out there do change with time, and what that means for our thinking. He also was the first person to do precision measurement science, and that is a spectacular contribution to our story. Now, what about this idea that the heavens can change with time? I mean, think about the possibilities now. That means that the universe may not have been the same in the past as it is now. And that completely opens up ideas about new questions. Can you imagine Ptolemy trying to ask questions about, I wonder what the universe looked like in the past? Oh, of course, that's a stupid question because it was the same. And that's it, game over. But now that you think, oh, things can change with time, and you could say, I wonder what the universe looked like in the past. Now you can think of ways to actually try to figure out how to ask that question of nature and do experiments. And then you learn new things that are going to make you ask new questions. So that was another big opening, mind can opener on the human brain. Okay, now armed with 10 years of precision data of the position of Mars and the other planets, Mercury and Venus and Jupiter and Saturn, whatnot, we can add to our story this great geometric astronomer, and his name is Johannes Kepler. Maybe some of you have heard of Kepler. Kepler knew about Tycho Brahe's measurements, and Kepler firmly believed in the Copernican view of the universe, that it was heliocentric, and he wanted to demonstrate it mathematically. So what he wanted to do was get a hold of Tycho Brahe's data. And so what he did is he basically got a cart and packed it up and walked all the way across Europe, all the way up to the island where, off of Denmark, where Tycho Brahe's Sky Dome observatory was. And he knocked on the door and said, hey, I want to be your mathematician and blah, blah, blah. And so, Tycho hired him, and he would give him little pieces of data now and again to work on. And the reason that he didn't really give him all the data was because, as you'll see in the video, one of the videos I have is called, it's video 3 called Kepler's First Law of Motion. It's mentioned there and shown in a little more detail that Tycho Brahe made up his own version of a model of the solar system, in which the Earth went around the sun, but all the planets and all the other planets still went around the Earth. And he wanted to prove that. And he knew that Kepler didn't want to prove that with the math. He knew that Kepler wanted to prove Copernicus's model, where all the planets go around the sun. So they were at odds with each other. Now, one day, Tycho Brahe died. He was a very colorful individual. He drank a lot of beer, as Danish people, some do. And he was having beer with the king and at the king's dinner table. And you may not know this, but when the king's sitting, you don't even ask if you can go to the bathroom. And you do not leave the king's presence unless you are given permission to withdraw, okay? Well, apparently he drank too much beer and pretty good at holding it, but his bladder burst. And then about 3 days later, very painfully, Tycho died. So Kepler was thinking, oh, this is great. I'm going to get all of his data. And so he asked Tycho's family, can I have the data? And they said, no, you can't have the data. So one of my favorite quotes about science is, forwarding science more than forwarding ethics, he stole the data. And that's true. Johannes Kepler stole all of Tycho Brahe's data, enough of it. He ran off with it, and then Kepler, Johannes Kepler, spent 10 years studying the data. Okay, so it took Tycho 10 years to accumulate the data, and then it took Kepler 10 years to analyze the data. Now we throw it into a supercomputer and have it done in a microsecond, but it took 10 years back then, okay? So what he learned was that he couldn't really get things to work the way Aristotle's part of Copernicus's model would say it should. What I'm referring to is the fact that the planets were orbiting the sun in circles and at constant motions. And in fact, he actually first realized he had to get rid of the constant motions, but he was kind of prepared for that because Tycho had always showed that things can change. So that meant the speed of the planet had to change, speed up and then slow down and then speed up. If he could allow for that, then he could get the data to match what would be a simple model. So that was very important, that he was open-minded enough to allow for changing motions of the planets. And that was because Tycho had found that one thing. So it's, it's a little step by step type of process you can hear in this story, okay? And then the other thing is that he finally realized he had to abandon the circles. So he had to abandon the constant motion and he had to abandon the circles. And that's what I got there in the red box. And that is very important because we get rid of the sphere as being the, most perfect geometric form. Therefore, the whole universe has to be, on spheres or in spheres or around spheres. No, that was gone. Now we can use another geometric figure, and it turns out to be the ellipse, and we'll talk about it in a minute. And we got rid of the constant motions. Okay, now, so let's talk about Kepler's first law, and that is the abandoning of the circle, and that the planets orbit on a curve that is called an ellipse. Okay, so here's a perfect circle. It has one focus point, and it's defined that all points along this curve are equal distance from that focus point. Okay, an ellipse is very similar, and there's a great little example of this in the movie clip called Kepler's First Law of Motion. And it basically has two focal points, and it's an elongated circle, if you will. And so these ellipses are defined such that if you take a string and you put a pin here, and you put a string tied there and a string tied there, and you put a pin there and you go around, then this curve will come out. And the idea is that the distance from focus point 1 to this curve plus the distance from focus point 2 to the curve point, the sum of that distance and this distance is going to be equal everywhere. So you pick another point, and so the distance from here to here plus here to here is the same as the distance from here to here and here to here. So it's the sum of those two that are always constant, that define the ellipse. Okay, so planets don't give a stitch about that, but that's what defines the shape of the curve. Okay, now what we'll see is that the sun is only at one focus point, and the other one is just a mathematical point. And so if this is the planet moving around the ellipse, and this is the sun here, and that's just a mathematical point, you can see that there are periods where the planet spends its distances close to the sun, and there are periods along its orbit where it's far from the sun. This distance here is the closest approach, and that's called the perihelion. Okay, peri for close to the sun. And the distant position here on the orbit is the farthest from the sun, if this is the sun, and that's called aphelion, or from the sun. Okay, so again, here's a diagram of this. You have an ellipse, and let's say the sun is at one of the focal points. There's nothing at the other focal point. The planet orbits in an ellipse. Okay, when it's at its closest approach, it's at perihelion. When it's at its farthest approach, it's at aphelion, or the farthest point along the orbit. And then you can see it goes along this sort of elliptical curve as it orbits around. So we have Kepler's first law. The orbit of each planet around the sun is an ellipse. But there's two parts to the law, with the sun at one focus. So if you happen to be taking an exam in a random astronomy course that you might take someday, and you get asked what is Kepler's first law, then I suggest you use both parts of it, okay? Kepler's law is that the orbit of each planet about the sun is ellipse. Part two, with the sun at one focus, okay? That's important because it tells you the relationship between the planet and the sun, okay? All right, I can't tell you how many times people leave out part two of that, so remember both parts, okay? Now, this gets a little bit more involved, but this is Kepler's second law of motion. He had three laws, but I'm not going to get into the third law. I think doing two of them is quite enough. Okay, now I love this law, sometimes called the law of equal areas. Okay, I'm going to read it to you, and it's not going to make any sense. And that's the beauty of this, why I love it, because it's just ridiculous. Okay. Kepler's second law, as a planet moves around its orbit, it sweeps out equal areas in equal times. How's that? Okay. Sometimes people say, if you draw a line from the planet to the sun, the line sweeps out equal areas along the curve in equal times. Okay, great. What does that mean? It basically means the planet moves at different speeds, at different locations in its orbit in a very, very well-defined way. And that is that, if you look at this diagram up here where I'm doing my cursor, when the planet is at perihelion, it's moving very quickly along the path of its orbit. And when it's out here further away at aphelion, it's moving at its slowest, okay? So I'm going to show you with my cursor what this looks like. We come along here, we're coming along fast, and then we slow down, slow down, slow down, slow down, and then we pick up speed again, and then we slow down again. And so this is the basic behavior of a planet. And it does it such that in certain equal time intervals, if you look at the slice of pie, if you will, that this area of this piece of pie, it would be the same over the same period of time where the planet's going fast as it is over the same period of time when the planet's going slow. So you can see here, if this is a 30-day period, we've gone fast along the curve, and this little line here has swept out a large area. So this is a short, fat piece of pie, if you will. And then as we come around here, we've slowed down. Okay, we're going slower. And so over the same period of time, we sweep out that much area. And okay, and so now we have a very long, narrow piece of pie. But it turns out that if you were to pick one of these pieces of pie, you're getting the same size of pie. This is exactly the same area as this area here, because the velocity along the path and the time are somehow linked together such that you get equal areas in equal time. And this is really a consequence of something called angular momentum. I'm going to talk about that again in a second. And so here's an example down here, which really shows it month per month, January to February, moving very quickly, a very short, fat piece of pie. February to March, a little narrower. March to April, narrower. Okay, out here where we're moving the slowest in a 30-day period, we trace out a smaller arc, but we have a very long, narrow piece of pie. And each one of these 30-day intervals, this area, they're all the same area. Okay, now this is the consequences of something called angular momentum. You know angular momentum very well. You see it in the ice skaters. They go into a spin with their arms far away, okay? And then they pull in their arms and they pick up speed real quick, and then they let their arms out and they slow down again. They're behaving exactly like Kepler's law. They are conservation of the momentum of their angular spin, okay? And it's very simple. The product of the distance out, okay, and the speed along which it's moving, you multiply those two numbers together. They're always going to be equal to no matter what they are, relative sizes are. Okay, so you're spinning around, you got your fist way out here, you know, it's about, say, 3 feet out. Well, that's a heck of a long arm, 2 feet out, and then it's moving very slowly. Then I pull it in, I'm going to be moving very quickly, but my distance is going to be very small. So I take this distance and this speed, I get a number, and I multiply them together. If I'm in here, I'm moving around really fast with this speed, I'm taking my small distance and my big speed and multiply them together. Guess what? When I multiply them together, I get the same number. And so this is a conservation principle. And this is what's happening with the planets. When they're further away, they move slower, okay, so that their distance times their velocity is equal to some number. And when they're closer, they're moving faster and their distance is smaller, and the product is the same final number, okay. I also have a video on this. There's a 29-second video here you can click on, but I have also a 3-minute nice little explanation. This young lady does an excellent job. She's got a highly produced astronomy shorts, and so stellar parallax. I'm sorry, the Kepler's first law and second law videos are from her, and they're really good. They're each about 3 minutes. Okay. So with Kepler, we see that we have dethroned the circle and the sphere. We have also had another situation where it really demonstrated that things don't move at constant speeds. They do change with time. Okay, so adding to Tycho Brahe's supernova and cometary observations, that those change with time and those were in space. Now you've got planets not moving on constant velocities, and they're not moving on spheres. So you're really starting to dismantle the Aristotle model, which still is reigning supreme because of the Roman Catholic power, and they're still persecuting people who are saying otherwise. Okay, even 100 years later, when you get to Galileo, they're still persecuting people for arguing this. And so the bottom line is we're slowly showing the people that want to hold on to Aristotle that there's too many flies in the ointment. You know, there's too much tension on this model of the universe, okay? Okay, so now let's talk about the 3 final nails in the coffin of Aristotle. And they came from Galileo. Now, in 2009, we had the 400th year anniversary of 1609 of Galileo pointing a telescope at the sky and seeing some of the things we're going to talk about. And this was, of course, a revolutionary in experimental science, and ushered in the final sweeping acceptance of the paradigm change, the revolution of the Copernican way of thinking. And so now you can see why Copernicus's thoughts were so revolutionary, because they opened up new questions, which opened up new ways of looking at the universe, which changed our view of the universe permanently. Okay. Okay, so again, though Copernicus' proposed heliocentric model was not yet accepted as better than Aristotle's, it seemed to only work. It fit Tycho's data. You couldn't have Kepler's laws unless the sun was at the center. You couldn't have this idea that the universe was changing because you couldn't have measured parallax if the sun was, if the earth was at the center. So all these things are coming together. But Galileo was the first to use the telescope. He's known as the father of modern science, not just because of his use of the telescope, but he did a lot of great work in the laboratory and developed ways to objectively measure the behavior of nature, like how bodies fall. You've heard of the experiment where he drops the glass and lead ball off the Leaning Tower of Pisa. As an experiment, asking nature, well, do they fall at the same rate or don't they? And then if they don't, well, I'll do some more experiments to find out why. And if they do, I'll accept that and try to figure out if I can figure out why that happens. I got news for you. We're still trying to figure out why that happens, that they both fall at the same rate. We're still trying to figure that out. It's called the law of falling bodies, and it's been at the center of every other following revolution that we're going to talk about. Okay, so he started an observational driven era and swept away the Aristotle and Platonic view of you think about things and use philosophy and ideals to figure out the world. Okay, let's start with his observations of Venus, which is up in the sky every morning to the east. If you happen to get up around 5 o'clock, you can see it up there as bright as the brightest star in the sky. Well, it's not a star, it's a planet, but it's really awesome to see. And he, with his telescope, could actually resolve the disk of Venus for the first time. Instead of seeing it as a point source, he saw it as a little world up there. In the same way that you can see phases on the moon, he was able to see phases on Venus, okay? What did he see? He saw what's down in this bottom chart here, okay? He saw basically that if Venus was between the sun and the earth, that he couldn't see it at all. Just like we don't see the moon when it's between the sun and the earth. It's what we call a new moon. And then we see it become a crescent, and that happens when it's at this angle with respect to where we are. And then first quarter, and you've seen the moon like that, where it's split in half like that. Well, that's because it's at a right angle with us with respect to the sun. Same thing when Venus is at a right angle there with respect to us and the sun. And then you have gibbous, and then full, and then what we call waning gibbous, and then third quarter, and then the final crescent that's waning, and then new moon again. He was able to watch this cycle. Now, that cycle is only going to happen if Venus is orbiting around the sun in an orbit that's inside of Earth's orbit. So this is observational evidence that you cannot explain in terms of Aristotle. It's totally inconsistent. It's a nail in the coffin. You just can't have it, because what would you see with Aristotle's model? You would see what's up here on the top. You would never see a full Venus or a gibbous Venus. You would only see crescent and new Venuses, okay, as Venus got in between us and the sun. So it was impossible to actually see these cycles periodically happening with Venus. And so this was one of the first nails in the coffin to really kill off Aristotle, as people were adopting and thinking that they should adopt the Copernican model with the sun at the center. Okay, the second thing that he saw were moons that orbited around Jupiter. Okay, you may think, oh, well, that's a really cool discovery, but why is that so profound? I'll tell you why it's profound. It's profound because all of a sudden now, you don't have just one center of things in the universe, that you can have multiple centers, okay? So now he's starting to show unequivocally that the sun is at the center, not the earth. And we all know that the moon goes around the earth, so that puts the earth at the center there. So that means there's two centers, but one's our center. So that doesn't count. And then you've got now Jupiter as its own center. And so what's to stop Saturn from having its own center, or Mars? And all of a sudden you've got this plurality of centers to systems in the universe. And this is a mind-opening thing that basically says the universe could be way more complex and have its own little closed systems. And this actually got people thinking that, in fact, maybe the other stars have planets around them too. And now you start to get into the question of, is there other life out in the universe? Could those other planets have living beings on them who are out there doing what we're doing, looking up to the heavens and wondering if there's other beings? So that all got opened up, okay? So this was published in 1630. A lot of this stuff he had for 30 years and didn't publish it because he was going to get in trouble with the church. And Galileo was in Italy, so he lived in Pisa, which is very close to Rome and within the strong arm of the Roman Catholic Church. Here are his original drawings, and he was able to show that from night to night, if we take these more modern view of these drawings and look at them here, that he was able to find 4 moons, which he called Io, Europa, Ganymede, and Callisto. They were eventually called the Galilean satellites, or the Galilean moons, but he wanted to name them after a rich merchant in Pisa so that he could get a lot of money for, you know, be the favor of this rich merchant, but that didn't stick. Anyhow, you can see that these move around. He was able to determine the speeds and the rotation periods, or I should orbital periods of each of these. And they, guess what? They follow Kepler's laws of this, doing elliptical orbits around their center, which is Jupiter, which is at one focal point. And they followed the second law, and they followed his third law, which we didn't talk about. So all of a sudden, you really got this very powerful observational system, which says that we are not the center of the universe. There's multiple centers to the universe. Now, I'm not going to talk about it too much, but around this time, there was a gentleman by the name of Giordano Bruno, and you should look him up, B-R-U-N-O, and just go to Wikipedia and read about this guy. He was a genius and a heretic, because his ideas were just not acceptable to the church. So what did they do? They burned him at the stake. Okay, so that's what you got if you were open about your thoughts with new scientific ideas. So Galileo kind of kept it on the down low for a while. Okay, so Venus has phases, Jupiter has moons around it. Okay, and last but not least, sunspots. Okay, it's part of why Galileo went blind. He charted the sunspots on the sun. So here's some of his pictures. Here's some sunspots. He's labeled them A through G or F or whatever. And he showed that they change with time. And this has 2 powerful implications. Number one, not only does it change with time, therefore Aristotle's idea that you don't have anything changing out there in the universe, again, is shot down. Okay, excuse me. And it also shows that the sun does not have a perfect, unblemished surface. Remember, Aristotle, perfect and unchanging. Okay, so now you have an imperfect surface of the sun, and it's changing with time. Okay, you have phases of Venus changing with time. Only can happen if the sun is at the center, and you have Jupiter following Kepler's laws, which only work if you have the sun at the center for the planets, and definitely was shown to be behaving that way for another center around Jupiter. All right, so all of this stuff was just too much for the Aristotelian model, and it finally collapsed in the 1600s under the weight of Galileo's final observations. Okay. He also looked at the moon and saw it had mountains and craters on it, so it was also an imperfect surface as well. Okay, so this is round 2 of the old dead guys that rock your world. Okay, and so, oh, that's going to be my secret password, rock your world. Okay, got it? Password, rock your world. Got it, okay. Now, Tycho Brahe used parallax to show that a comet was outside the Earth's atmosphere, and that a supernova was outside the Earth's atmosphere. Again, these were changing things. He showed that things out there in the universe could change with time. Another tension on Aristotle's model, okay? He made thousands of precise measurements and positions of astronomical objects over a period of about 10 years. Johannes Kepler came along, totally firmly believing in the Copernican heliocentric model. That's a lot of faith to spend 10 years working out some math based upon that idea. What if he had chosen Tycho Brahe's model and spent 10 years and couldn't get it to work? Eventually, he'd probably have to abandon it and say it's wrong and go back to Copernicus. Okay, but he didn't. He stayed with Copernicus, spent 10 years working on the mathematics of the data from Tycho Brahe, came up with Kepler's first law: planets orbit along an ellipsis with the sun at one focus, and Kepler's second law, which is that planets sweep out equal areas in equal time. Basically, he discovered the constant of angular momentum, but he didn't understand it as that at all. Waited for an Isaac Newton in the 1700s, late 1600s, sorry. And then Galileo in 1609 looked to the heavens with a telescope, discovered the moons of Jupiter, discovered that there were phases of Venus, and discovered changing sunspots. And all those contradicted Aristotle's little perfect and unchanging model, and the fact that the Earth was at the center. And so all that's gone, and Galileo really put the final nail in the coffin, put Aristotle's theory in the ground, and he became known as the father of science, and mostly the father of science on account of the fact that he also did a lot of scientific experiments and really wrote the book on how to science. So that brings us to some ideas about how to science that will be coming up. Okay, so the Copernican Revolution, we have Tycho's precise observations that led to Kepler's planetary motions with the sun at the center. That led to then Galileo's observations through the telescope. And this rekindled the debate of the plurality of worlds, as I was talking about. And therefore, the debate for life elsewhere in the universe blossomed dramatically. Okay. And then I mentioned that Giordano Bruno was burned at the stake for some of these ideas. He was fiercely promoting them, and the Roman Catholic Church had to silence him from their point of view. Galileo was taken before the Pope and was put under house arrest and spent the rest of his life in house arrest. He had to take back all of his statements that he had made and declare that he was wrong, and declare that he believed that the Earth was at the center of the known universe. But in the end, these ideas went out. And so we see that this whole process, where you have the original seed of an idea from Copernicus, then with that opening minds to do some observations to look at it more deeply in ways that hadn't been thought of before, then coming together to really show that the old view is completely wrong and can't make any sense of it when you look at the new observations that developed, many of which to new technologies. You had Tycho Brahe's big spheres and all that. That's high technology for his day. And the telescope, that's new technology. You bring that in, get new observations, and you push on these things. You see the little flies in the ointment, and you basically show that those little things are telling you that things were very, very wrong, and you sweep them away and you get a whole new view of the universe. And so now we have a view that allows for the possibility of other solar systems and planets going around other stars, and therefore life being on other planets out there in this plurality of worlds. So that was a huge part of the implication in terms of our study in this class for life in the universe. Okay, we are down the home stretch. Thank you for watching these long lectures. They're usually supposed to be a Tuesday and a Thursday lecture, each one an hour and 15 minutes. So you can see they're still shorter than if you had come to class, but they're long, and that's why I recommend sitting in 2 sittings. Okay, so we're going to end with the hallmarks of science, and then we're going to end with the process called the scientific method, if you will, or hypothesis-driven science, the recipe I was telling you about at the beginning. Okay, the three hallmarks of science as we know them today. Okay, first of all, modern science seeks explanations for observed phenomena that rely solely on natural causes. Okay, we've given up the fact that lightning is a weapon being thrown by a god from the top of a mountain. Okay, we're letting that go. And we're saying, hey, lightning is probably a natural phenomenon that's created by something else. Oh, well, it's created by electrons grouping in clouds and releasing their charge. And so we start to back it out more and learn more about what's going on. Later on, we might want to understand what electrons are and how they group. But in the meantime, step by step by step. Okay, so that is this blue circle here, seeking explanations for observed phenomena that rely on natural causes. Okay. It's also driven on a belief system about the world, and that is simple, beautiful, and understandable. And that has been codified in this amazing quote by Albert Einstein, that the most incomprehensible, sorry, I've been talking too long. The most incomprehensible thing in the universe is that it is comprehensible. That's a statement about the human mind as much as it's also a statement about the universe being something that is, organized and has order to it. Okay, and that in itself is incomprehensible. I mean, as a scientist, I often ask, why is there anything at all? Why is there a universe that exists? Period. Why is there organized matter and energy? Okay. So I just want you to also remember from this one that the simple and the beautiful stem all the way back from Plato's belief, and that is still ingrained in our way of doing science. Okay, number two, science progresses through the creation and testing of models designed to explain observations, and these models should be as simple as possible and be consistent with the rational understanding of the other aspects of science. Okay, so it's got to fit in, and it's got to be reproducible, observable, and reproducible, okay, so that it seems that it's not an effect that we have created, but that it's something that nature's telling you that's the way she is, okay? And this process of testing models is a way of refining our views. Okay, that's what we call refinement. Ptolemy's circles on circles on circles was a refinement of Aristotle. Okay, a wrong theory that he refined, but nonetheless, that's the refinement process. Okay. The idea of it being simple as possible is left over from the simplicity and the beauty arguments. Okay, this has been codified in a principle called Occam's razor. Okay, William O. Occam. Okay, and quite simply, you could say that this principle says that if you've got two competing ideas, models, hypotheses, theories about the way the universe works, you should adopt the more simple one because it's probably going to be closer to what the truth of the situation is. Remember, all of our models are incomplete. All of our theories are incomplete. There's always something that nags us about them that we know they're not quite getting and capturing everything about nature. So there's a deeper fundamental behavior or truth of nature there. But the simple model is the one to probably probe on and push on because it's going to help you uncover that information more. And we truly believe that nature is more simple than more complex. 9 circles on circles going around in perfect motion forever is too complicated. Lines and lines and lines and lines of mathematical calculations versus the simple idea of Copernicus, where retrograde motion was just an apparent optical effect, optical illusion, if you will. It's not an illusion, but an apparent effect rather than a physical loop-to-loop itself of the planets. Okay, Occam's razor. The simple principle is the one you should adopt and test. Is probably closer to the underlying truth of nature. And number three, the scientific model should be testable. So you need to be able to make predictions. Okay, you need to make a model that's going to say, not only does this describe observations I've made, but it's going to say what should happen. You know, like I told you, Ptolemy's model of all those circles on circles, he basically said, I can tell you where Mars is going to be in 25 years. And he, calculate that out. 25 years come by, if Mars isn't there, then he failed the test. Okay, so we got to refine him. We got to refine his model or throw it out, one of the two. Okay, so you can see the process that's beginning to have developed here in this method. Okay, so we must be able to always envision further validity checks. Okay, because eventually you push on it until it breaks, and we love it when it breaks. We're not all about getting it right. We're about getting it more right, I guess, as time goes by. So that's number three down here. Makes testable predictions about the nature of phenomenon, and predictions do not agree with observations. The model must be revised or it must be abandoned. Okay. Okay. It is very easy to find an observation that's going to throw out your model, okay, or at least make you change your model or your hypothesis, okay? Just because you do an experiment, you have a prediction, you do an experiment, and just because you do that and you made the right prediction and you get the experimental answer of your prediction, doesn't mean you're right, okay? Because there's things further down the road that are more subtle that it might get wrong. And that might cause you to have to abandon the model later as you get more precise in your measurements, okay? All right, let's move to the last slide, 22 out of 22. Congratulations for getting here. And I'd like to introduce you to Dad, the father of science, Galileo again. And this is what we call the scientific method. So now I know this has been a long lecture, and I know that you're probably intellectually tired and listening to me, but I think you need to at least come back and listen to this slide, because this is the pinnacle slide of the lecture. And so you really should sit down when you're fresh and follow it, okay? All right, so let's talk about this. You're a human being and you observe something, okay? And so it makes you wonder something, gosh, the stars go across the sky every night from, rising in the east and setting in the west. And so does the sun, and so do these other little planets, and so does the moon. I wonder why that happens, okay? And so you make a hypothesis. I think that the stars are on a big sphere, and the sphere rotates around the Earth, which is at the center and unmoving, okay? So that's going to make some predictions, okay? I think the planets are doing that, okay? So, okay, the planets are going around these spheres that we talked about at the very beginning of the lecture, okay? Well, that's going to make a prediction. That's going to make a prediction that the planets always go at a constant speed across the sky. You never see them reversing their motion on the sky and things like that. That's a prediction, okay? And then you look up and you go, wrong. It turns out that they do a loop-de-loop, okay? I've seen it now, it's called retrograde motion. So you've made this prediction and you do an observation, you watch the planets, you measure where they are every night, and you go, no, we got a problem here. The planets did a loop-de-loop. So that means that my hypothesis needs to be refined. Or if I can't refine it, I can't figure out how to refine it, reject it. So we come along here, and really most of what science does, 99.9999999% is it refines the current working model. So we come along this path, which is the test does not support the hypothesis. I saw retrograde motion of the planet. My hypothesis predicts that the planet should go straight along across the sky, constant motion. Okay, so I got a problem. My test does not support the hypothesis, my observations of the prediction. So I come back up to my hypothesis and I shake I put my fingers on my chin and act smart, and I say, I'm Ptolemy, and I'm going to put a loop-de-loop on the sphere of Mars, and I'm going to make it go around. you know. And so he kept doing that, and he kept getting kind of a little bit wrong predictions. So he put nine of those little loops, and he finally got, I got it pretty good. And then he passed away, and it stayed for that way for 900 years. Okay. Well, then you got things that are other predictions, like you shouldn't see comets out in space. They have to be in the atmosphere because they're changing. You have other predictions that supernovae, those stars that go off, they better be in the Earth's atmosphere because they can't be out there changing. The orbits of the planets, when we get better measurements of them, they better be on circles, they better be in constant motion. But what happened with all that? They kept being wrong. They kept having to hypothesize it. So in a sense, you get finally to the point, a breaking point where you say, I gotta trash this whole thing, this whole geocentric thing. It's not happening. I gotta trash it. So you trash that and you get a new model, and the new model makes you look at the world differently. It's a shift in their paradigm. You had a paradigm where the Earth was at the center and that everything was unchanging, that the universe effectively had to be made for humans. There was no room for any other types of living planets with life on them because the universe was built for the Earth and it's at the center. Now all of a sudden, you just moved it a little bit off center to orbit around the sun, but then you found other planets that had moons around them. They had their own centers. Now you're thinking the stars have that, and your whole mind boggly wide goes broad and wide open, and you start getting all kinds of new questions that you can ask. So Galileo made a whole bunch of new observations that had to be, added to the observations of Aristotle and Ptolemy. And that developed new questions and new hypotheses. And now we have the heliocentric model of the universe, in which the sun is at the center and the Earth goes around it and spins on its axis. And we keep testing on that. We keep testing on that. And so far, we've had no evidence that says the Earth is not spinning on its axis. We have no evidence so far that's contradictory to any predictions that, the phases of some of these things are wrong, or the overall behavior of the system is not following all the predictions. And so we're very happy with the idea that the sun is at the center of the universe, that the Earth is round, that it's spinning on its axis. Now, there are people out there called flat earthers. There are people that just won't accept science. They reject it. And so I don't know where they are on this diagram, because they just completely ignore all of the evidence. They come up with a hypothesis, like the Earth is flat. It's going to make some predictions. How they explain away all the observations that don't match and somehow put them back on this loop is beyond me. But that's what you call confirmation bias. And it's scary that people can lie to themselves this way. All right. So in wrapping up, we've talked about this long story, a long story from Plato and Aristotle all the way through to Galileo, that involved a paradigm shift with the thoughts of Nikolai Copernicus. And we showed how observations keyed into these things. When we go to our next set, modern science, we're going to talk about what happened from the 1700s on through to the current time. And we're going to talk about how our ideas that space and time are constant entities, and how they actually are fluid and change, and how time passes, or what this curvature and behavior of space is around you. These depend on whether you're near a massive, highly energetic object or far away from one, or whether you're moving fast, okay? And this is all completely a big paradigm change. And then we're going to talk about Einstein's theory of how space and time change and are warped, and how that really gave us gravity. So before we can talk about that version of gravity, we'll be talking about Isaac Newton and his form of gravity, a theory which is so correct in so many ways that it predicts perfectly 99.999% of everything we need it to, but there are flies in the ointment. Then Einstein came along, paradigm shift, changed the whole picture, and now guess what? We've been pushing on Einstein for 100 years, and that's what's going to be part of our next lecture. And guess what? we're starting to see the flies in the ointment of Einstein after 100 years. So it's getting interesting again. We're in a cycle, people. We're in a process, okay? You are at the tip of humanity in the current time. You're on the tip of a spear that's moving through and getting more knowledgeable and better. And what has allowed this to happen? This method of science that we're talking about, okay? And there's something about the modern culture that seems to be more and more rejecting the wisdom that's, or I should say the worldview that's developed through the scientific method. Okay, I hope you remember the magic word. Okay, you take the attendance quiz for the magic word, and then watch the videos. We got retrograde motion, stellar parallax, Kepler's laws, and then a nice movie which summarizes the Copernican Revolution basically in 15 minutes. It's a great little show that summarizes all of the points we tried to make here. Then we'll move on to modern science when we get to the next week. So you all take care. Don't forget Tuesday and Thursday, we have the optional office Zoom hours from noon to 1. And Canvas message me or use the discussion board if you have some questions. Okay. And once again, I forgot to just put myself on full screen while I say all that stuff at the end, but maybe I'll get it right by the time the class is over. Take care, everybody.